Good day. Welcome to this presentation based on differentiability. In this video, my intention is to set the groundwork for differentiability and help you understand the definition, the theorems that is associated or that are associated with differentiability, and also the exceptional cases that we need to be aware of when we deal with this topic. All right? So without any waste of time, let's go for it. Let's start with the definition, okay? When we say a function is differentiable, it means that the derivative function exists, okay? At that point where our interest is at, or our point of focus. So if a function f is differentiable at a point, say x equal to b, then f prime of b exists. Okay? Furthermore, a function f is differentiable on an open interval, say CD, if it is differentiable at every number in the interval. Okay, let us use a sketch to talk about what we are saying here. Let's call that our open interval CD, okay? That is our open interval CD. You'll recall that we have interacted with derivatives before under first principles, and also when we did rules of differentiation, okay? Actually, there'll be an end screen button at the end of this video that you can click on to go back to those videos to remind yourself as to the definition of derivative and actually the gradient function and what that stands for and what it means. Okay, so when we find a derivative function, we have used tangents at that point to approximate the rate of change. So if you look at any point here, we can draw a tangent, okay? Suppose this is a smooth curve, there are no sharp corners or anything of that kind, okay, and discontinuity. So if it is differentiable on an open interval CD, then it is definitely differentiable at every point in that interval, right? It means at every point there can be a tangent that can be used to approximate the rate of change of that function, okay? So this takes care of the definition of what it means for a function to be differentiable. And remember that the derivative, okay, f prime of x is equal to limit as the horizontal distance approaches 0 of f of x plus h minus f of x over h, right? So we're going to work with the simplified version of this when we do the test for differentiability of functions, okay? So how do we determine if a function is differentiable? Let us talk about that. Okay, so now we come to the differentiability test of functions, and to determine if a function is differentiable, two conditions must be met, and they are as follows, okay? To prove that a function, suppose f of x is differentiable at a point x equal to a, first condition is that f must be continuous at x equal to a, right? And limit as x approaches a from the left of the derivative of f must be equal to the limit as x approaches a from the right of derivative of f. Okay, so the condition is that f must be continuous. So we can guess if f is not continuous at that point, definitely it won't be differentiable at that point. So this is a primary condition for this differentiability test. Okay, so this is what we need to work with when we work with differentiability of functions. And actually this leads us nicely to the theorem that says the following. If a function is differentiable at x equal to a, then the function is continuous at x equal to a. Okay? The converse of this theorem is not true. If a function is continuous at x equal to a, it does not necessarily mean that it will be differentiable at x equal to a. Okay? I will give you 3 examples to convince you of that the converse is not true. So when will a function fail to be differentiable? I have 3 cases to help us understand those different situations, and let's deal with the first one. Case 1. So here's an absolute value function, and from left to right, if we track the progression of this function or the behavior, we can see that it is decreasing, and it's increasing after point A. Now, this point is where we want to test for differentiability, but this is not a turning point. This is a corner, or if you like, you can call it a kink, right? So we cannot accurately and really approximate using a tangent, right? Because this is not a smooth curve at that point. We cannot have a tangent. So there's no tangent that we can draw to this point or this curve here to help us approximate the rate of change at that point. All right. So therefore, we say that function or this absolute value function will not be differentiable. As much as it is continuous throughout its domain, well, from negative infinity to infinity, at that point it won't be differentiable. Okay, because the fact that we cannot produce a tangent that can approximate the rate of change. So let's go to case 2. Here we can clearly see that we have discontinuity. Okay, remember we spoke about the gap. So whenever we have a gap, we have a jump discontinuity, and if your function is not continuous at that point, in this case point A, definitely don't be differentiable, because the primary condition is that you want the function to first be continuous before you test the one-sided limits for your gradient function. Okay. Case 3 is when you end up with a vertical tangent. You know that vertical lines have an undefined gradient, and therefore it becomes a futile exercise to talk about a gradient function if you have a vertical line. So if you check the progression of this function, it's decreasing, right, in terms of its rate of change. And if you get a collection of tangents that will accumulate or be present, you end up with a tangent at that point that is vertical. And then you now have tangent or tangents with an increasing gradient, because now it starts to increase. But now at this point A, when you have a vertical tangent or this type of portions in piecewise defined functions or other types of curves, then you know that at that point, because the gradient of a vertical line is undefined, that function won't be differentiable at that particular point as well. Okay, so this takes care of the 3 cases that you need to be aware of in terms of the type of curves that will fail to be differentiable at So this takes care of the presentation to lay the groundwork, and in the next two videos there will be questions that we'll be answering as examples to see how we approach questions based on differentiability. Okay, so I'll see you there, and thank you for tuning in.